Hello, this is Professor Keen. Today what I'll be talking about is planetary motion. This is from chapter 26 in A Student's Guide to the Great Physics Text, volume 2. And in this chapter, we talk about book 3 of Newton's Principia. And this chapter is where Newton reminds us of the current state of affairs, the current belief about the system of the world. And by that he means the configuration or the shape of the solar system. So before I start talking about Newton's beliefs, I should probably give you some background about the current state of affairs. So this is something that I spend quite a bit of time talking about in my Physics 101 class, my course on Introduction to Astronomy. So I'm going to give you a very brief outline here, but hit some of the salient, most important points. So Newton, remember, was writing this in about 1687. That was the first edition of his Principia. What had happened in the immediate history, very recently, is there was a transition from a geocentric to a heliocentric worldview. And this is really ushered in by Copernicus. Copernicus in 1543 wrote a book entitled On the Revolutions of the Heavenly Spheres. And in this book, what he did is he argued that all of the planets were riding on circles or spheres around the sun. So the sun was at the center of the universe. He would say the world. We would now say the universe. He believed the sun was at the center of the universe, and the planets were all revolving on these spheres around the sun. This was not a completely new view. Okay, so there were ancients that believed that the Earth was one of the planets going around the sun, particularly the Pythagoreans. The Pythagoreans were around before the time of Aristotle. Aristotle was about 300 BC. The Pythagoreans believed that the Earth was one of the planets. But Aristotle argued against the Pythagoreans. Aristotle argued that the Earth was at the center of the universe. That's the geocentric worldview. So it wasn't like everybody believed that the Earth was the center up until Copernicus. There were a significant number of people who believed that the Earth was a planet, but Aristotle, and then after him Ptolemy, presented what I think were fairly convincing arguments that the Earth should be considered to be at the center. And that viewpoint that Aristotle espoused and Ptolemy espoused against the Pythagoreans back in ancient Greece, and then during the time of the Roman Empire, in the case of Ptolemy, was what persisted throughout the Middle Ages. And in fact, Ptolemy's book, the Almagest, was the most popular astronomy book in the history of the world. It was used from the time of Ptolemy in the 2nd century AD up until basically the 1500s, the time of Copernicus. And that taught geocentrism. So when Copernicus came on the scene and wrote his book on the revolutions of the heavenly spheres in 1543, he argued in what he thought was a convincing way that we should reorient reconfigure the solar system, our model for the solar system, and consider the sun to be at the center. Copernicus, by the way, was a conservative in the sense that he wanted to retain as much of the Aristotelian ideas as he could. He simply wanted to assign a new body to the center of the universe. He wanted to put the sun rather than the Earth at the center. Significantly, he believed, just like Aristotle, that there were enormous spheres, kind of crystalline spheres, that were carrying the planets around. He just thought that these spheres were centered on the sun, unlike Aristotle, who believed that those spheres were centered on the Earth. So that brings us up to about 1543. Then comes Kepler. So Johannes Kepler was a Lutheran theologian. Well, he wanted to be a theologian at first, and then he decided to become a mathematician and a scientist. And what he did is he worked for a man named Tycho Brahe. Tycho Brahe was a Danish astronomer, probably the most famous astronomer of his time in the 1600s. Tycho Brahe was a wealthy nobleman who owned an island and built an observatory, probably the most sophisticated astronomical observatory that the world had ever seen at that point. And Kepler was a student of his, and when Tycho Brahe died, Kepler inherited all of his astronomical tables and his research, all of the data he had collected over decades. And when Kepler was analyzing the data that Tycho Brahe had collected, he found that it would be a better model of the of the planets to claim that the planets move not in circles around the sun, but they move in ellipses around the sun. Now, this might sound like a very minor change. After all, he, just like Copernicus, believes that the planets go around the sun. The only difference here, or one of the main differences, was that Kepler believed they moved in ellipses around the sun, whereas Copernicus believed that they were moving in circles because they were carried by these celestial or heavenly spheres around the sun. So again, this sounds like a minor change, but in fact it was a major change. Why was it a major change? Well, because you have to understand why Copernicus believed that the planets were moving in circles around the sun. The idea was if there were enormous crystalline spheres, so to speak, on which the planets were riding, Copernicus believed that the natural motion of spheres was circular motion, just like Aristotle taught that the natural motion of spheres was circular motion. It was in their nature to move in a circle. So as long as the planets were riding on these spheres, kind of like a rock wedged in the tire as the tire is rotating. You can think of the planet as kind of like the rock that's wedged in the tire, and the tire is this crystalline sphere rotating around the axle, and the axle would be the sun. As long as you believed that these spheres, their natural motion was circular, you did not need to come up with any other physical explanation for the motion of the planets. So when Kepler found that the planets in fact are moving in elliptical orbits, it really threw that entire system out the window, because an ellipse is not a circle, and so its natural motion is not circular motion. It doesn't have a natural motion. And so what Kepler did is he said, if we can't rely on this Aristotelian view that the planets are riding on spheres around something because it's their natural motion, we must find another physical explanation. And this is really what Kepler tried to do. He said, whatever laws we come up with to govern the motion of things here on Earth, like falling objects and moving magnets and so on, those are the same laws that should apply in the heavens. That is, they should apply to the celestial objects, the planets and so on. And we really need to come up with a new physics, a new understanding of the motion of objects. So Kepler's reevaluation of the data that showed the motion of the planets really ushered in a reanalysis of how we even think about the motion of objects, both in the sky, in the heavens, and here on Earth. Okay? Now, Kepler speculated quite a bit about what the cause of the motion of the planets would be. And he thought that the sun, which was at the center, was emanating some kind of force from it, kind of like a magnet, like a magnetic force. And as the sun was spinning around, these rays of magnetic force were kind of like a whirlpool dragging the planets around in circles. So he identified the sun as a source of motion of the planets, but he identified that the force as more like a magnetic force, so to speak. He does say that he was inspired by the work of William Gilbert, who had just published his famous book On the Magnet in 1600. So those of you who have taken my Physics 202 class will have read some sections of William Gilbert's On the Magnet. William Gilbert's work on magnetism did in fact influence Kepler, and Kepler thought that magnetism was the cause of motion of the planets. Okay, so let's take another few minutes to explore the ideas of Kepler. Specifically, we're going to look at Kepler's 3 laws of planetary motion. These are not to be confused with Newton's 3 laws of motion. These are Kepler's 3 laws of planetary motion. And these Kepler's 3 laws of planetary motion, then, are going to be invoked by Newton when he develops his law of gravity. So I'm going to turn off my webcam and draw some pictures that illustrate Kepler's 3 laws of planetary motion. Okay, so let's talk about Kepler's first law of planetary motion. Let me get my pen out in just a moment. Okay, so Kepler's 3 laws of planetary motion. Again, not to be confused with Newton's 3 laws of motion. Kepler's. Okay, and this, by the way, is these were articulated by Kepler in his book, The Epitome. This is the reference, Epitome of Copernican astronomy. It's kind of his re-evaluation of Copernicus's worldview, and I frankly don't remember the date in which this was published. Let me just throw out the date. I want to say 1640s, but I don't recall exactly. Copernicus was 1543. Kepler wrote this in the 1640s, I think, 1643 maybe, and then Newton writes his Principia in 1687. So that gives you some of the timeline here. So what are Kepler's 3 laws of planetary motion? Again, we spend more time about this in my Physics 101 class, my Intro to Astronomy. So I'm just going to briefly go over these with you because they're going to be useful in understanding Newton's universal law of gravitation. So Kepler's first law. The first law is that planets move in ellipses around the sun, and the sun is located at one of the foci of the ellipse. Okay, so if I were to draw a picture, you can imagine that this would be the trajectory of a planet around the sun. So the sun, I'll make it yellow, the sun is located at one of the foci of the ellipse. And the planet, let's make this Mars. We'll make it red. So here's Mars. Each planet has a symbol. The symbol for Mars is a symbol for male. There you go. So Mars is moving in an elliptical orbit around the sun, but so too is Jupiter, Saturn, Venus, Earth, and so on. So they move in ellipses around the sun, and the sun is at one of the foci of the ellipse. You might ask, well, people usually do, well, what's at the other focus of the ellipse? Because remember, an ellipse has 2 foci. Well, nothing. It's just the sun is at one and there's nothing at the other. Well, maybe there's dust or something in space, but there's nothing of importance at the other focus. Remember, by the way, if you don't remember how you construct an ellipse, well, there's several ways of describing an ellipse. One of the ways to think about an ellipse is, let's suppose you had, you can make one right now. If you have 2 pencils, you put 2 pencils down on your desk. These are the 2 pencils. It's kind of a top view pointing at the desk. And you take a loop of string, and this loop of string, you tie it around the 2 pencils, and you take a 3rd pencil and you pull the string tight. So this would be your 3rd pencil right here. And what you do is, while pulling it tight, you simply go around like this, and the curve that you trace out, that will be the ellipse having those 2 foci. And so strictly speaking, an ellipse has the sum a plus b, the distance from this pencil point to this, and the distance from the pencil point to this, a plus b equals a constant. So this is maybe just a little bit of reminder for you about how to construct an ellipse. Anyhow, that's not that important. The important point is that Kepler, in analyzing Tycho Brahe's meticulously collected data over many years, he found that the planets, in fact, do not move in circles around the sun, but in ellipses. These are also, to be sure, fairly squashed ellipses, not squashed, they're pretty circular ellipses. They're pretty close to a circle. Only Mercury has a very squashed ellipse. The other planets are fairly circular orbits, but nonetheless, they are not circles, they are ellipses. Okay, that's law 1. What about Kepler's second law of planetary motion? Well, if you look at a planet as it's going around the sun, and you draw a line from the sun to the planet, we'll call that a radius, although it's not technically a radius because it's not a circle. But if you draw a line from the planet to the sun and you move it around, we will notice that that radius sweeps out equal areas in equal times. So I'll write that. Equal areas are swept out in equal times by a radius drawn from the planet to the sun while executing its orbit. Okay, so if I were to draw a picture of this, so again, I'll draw an ellipse like this, kind of exaggerating the ellipticity of it. We'll put the sun here at one of the foci of the ellipse. Okay, here's the sun. Let's make it nice and yellow. And we'll use Mars once again. So for instance, if you were to put Mars right here and then wait 1 month, Mars, let's suppose, moves that distance. Okay, that's during 1 month. During 1 month, the planet moves from there to there. And if we were to draw a radius from the planet to the sun, that radius is going to sweep out some area right here. Okay? Now, if you wait a while until Mars is over here, it's going to be moving still. And during 1 month, it's going to move, let's say, from there to there. This is 1 month. And if you were to draw a radius from the sun to Mars here, and the sun to Mars here, and you were to find the area swept out right here, this area, A2, and this area, A1, are equal. That is, during equal time intervals, 1 month, the area swept out by a radius drawn from the sun to the planet is equal. And it doesn't matter whether you choose 1 month, or 1 day, or 1 second. During any equal time intervals, equal areas are swept out. By the way, this is going to be an extremely important observation because Newton is later going to invoke this as evidence that there must be a centripetal force pointing toward the sun. So you might look back at Newton's proposition 2, theorem 2, that's going to imply that there is a centripetal force. Kepler himself didn't recognize that, but that's something that Newton is going to highlight and use to develop his universal law of gravitation. Okay? Let's move on to Law 3. Law 3 is a little bit more mathematical. It compares, it says, let's suppose we're looking at Mars's orbit around the sun, and we're also looking at, let's say, Jupiter's orbit around the sun. Well, you could measure how much time it takes Mars to get around the sun. That would be the period of Mars's orbit. And you could also measure the time it takes Jupiter to get around the sun. That would be the period of Jupiter's orbit. And you can compare those two periods, and Jupiter's is going to be longer than Mars's. But they're not. It's not just longer than Mars's in kind of a random sort of way. It follows a particular mathematical relationship. And here's what that mathematical relationship is. Kepler says that the periodic orbits, the periodic orbital times of any two planets, so this could be Mars and Jupiter, it could be Jupiter planets, or it could be Venus and Mars, it could be Venus and Jupiter, of any two planets, are in the, here's this word again, the sesquiplicate ratio. I didn't make this up. The sesquiplicate ratio, that's a 3/2 ratio, or the 3/2 power. The sesquiplicate ratio of the semi-major axes of their ellipses. Okay, so I'll draw a couple of pictures just to clarify what we're talking about here. So let's suppose we're talking about Mars's orbit and Jupiter's orbit around the sun. So I'm going to draw the sun right here. Okay, and let's say Mars is going around the sun. Oop, that's not where I wanted Mars. Mars is here. Okay, and then Jupiter's orbit, let's put Jupiter's orbit right here. I think that's a symbol for Jupiter, I forget. Okay, so it takes Jupiter a time t1 to go around the sun, and it takes Mars a time t2 to get around the sun. And what do we mean by the semi-major axis of the ellipse? Well, if you take a line across the ellipse, in this case, and across this ellipse in this case, the major axis is the distance from one edge of the ellipse to the other. The minor axis is the shorter distance across the ellipse. So if you compare these, this would be the major, it's kind of at a funny angle here. I should have drawn it a little more horizontal, but you get the point. This is the major axis of Jupiter's ellipse. This is the major axis of Mars's ellipse. The semi-major axis is half of that, okay? So what he's claiming here is that if you compare the orbital times of Mars and Jupiter, they're going to be in the same ratio as the 3/2 power of the ratio of the semi-major axes of these two. So A1 would be the semi-major axis of Mars, of Jupiter's orbit, and A2 would be the semi-major axis of Mars's orbit. And this law happens to hold for any two planets that you consider. If you compare the orbit of the Earth to Venus and compare the semi-major axis of the Earth to Venus, the ratios happen to obey this law. This is Kepler's third law of planetary motion. Why does this hold? Well, Kepler really wasn't sure. He just said it's kind of a neat empirical law. Now, why is this going to be important? Well, because if you remember back to Newton, I'm giving you a heads up here, Newton's proposition 4, theorem 4, and specifically his corollary, I think, 6, this is what you're exploring in laboratory this week, he said that if any two orbiting bodies have periodic times that go in the ratio of their radii, or the semi-major axes, to the 3/2 power, then we can infer a specific kind of centripetal force is acting on them. More specifically, we can say that the force pulling them in is a 1/r squared or an inverse squared kind of law. So while Kepler simply noticed these three empirical relationships, or these properties of planets orbiting the sun, what Newton is going to do is he steps in, develops a mathematical apparatus for evaluating this, and develops the universal law of gravitation to explain Kepler's three laws of planetary motion in a way that Kepler was unable to. Okay, so we've just talked about Kepler's three laws of planetary motion. Before that, I talked about some of the history of the geocentric and heliocentric worldviews. And the next time we get together, we're going to jump back into Newton's Principia and talk about his phenomena, where he's kind of reminding us about the state of affairs in astronomy at the time.